algebraic groups. And invariant theory. Yeah, so of course with invariant theory you have partly, and with algebraic groups you have partly so you should already know some notions, and so I shall give you first of all examples of algebraic groups that we shall understand with what we will encounter. So the first example is of course GLV. So the invertible matrices in so V is a vector space over the field. So here it is usually one takes algebraically closed field. If you want to reduce some problems to non-algebraic closed field, you just look at what happens in algebraically closed field and then try to understand what happens if you have some subfield. And if you are in most cases, so usually we shall assume that characteristics of the field is 0, but it is because in characteristics P the groups behave quite differently. So it is some kind of problem. So GLV is just in the set of, so the just you consider the operators from V to V, and you consider invertible operators. Yes, so invertible matrices. Yeah? And here already you know, for example, how you can, so what is the example of the action that will be also quite important for us in our future. Yeah, so as for just examples of algebraic groups, there are also some groups with some additional conditions. So these are groups like ON, SON, SLN, and SPN. And these conditions usually come from the following. So here you can, for example, you can fix on V, we can fix a quadratic form. Or better to say symmetric, because it is different in characteristic 2. So symmetric bilinear form. And or we can use, so here for this group we shall use symmetric bilinear form. For this group, in order to define this group, we use skew-symmetric bilinear form. So bilinear form is just the corresponding map from V times V to K, so which is K linear in each argument. And so if it is here you have condition of symmetricity. Here you have condition of skew symmetricity for the bilinear form. And how you define this group? So ON is just the group that preserves this form, simply saying that these are elements of GLV, such that G times V. So you apply the operator, and you should have the same value of on this form. So in some sense, the form plays the role of invariant, and it doesn't change under the transformations of this special type. And if you you define SPN just similarly, but you take a skew symmetric form, so such that GW is equal to VW for skew symmetric form. And so as for this group, so this you have an additional condition that it preserves the orientation. So SON is just the group of orthogonal transformations. So this is called the orthogonal group. This is called symplectic group. This is called orthogonal group. So this here you have additional condition that the determinant of G is equal to 1. And here, if you want to discuss SLN, so just SLN is just the elements of GLN, invertible matrices. Yeah, so just you can pick up the elements of. So for matrices and Bayes matrices, I will just denote by the set of endomorphisms of V is the set of linear maps from V to V. And so these are just the set of endomorphisms that have determinant equal to 1. Yeah, so what should be seen from the, so this is just a basic set of examples. You have, most of you have covered the standard course on geometry. Even I see the participants from that course. That I was a seminarist. So you see that so this is particular examples of algebraic groups, and what common in them. So just these groups can be defined by polynomial equations. In matrices, in the set of matrices.
You missed, can we define it?
Yeah. Thanks. Why? In the set of matrices, just and Bayes matrices. So notice that yeah. So what about so that's why we come to the notion of a fine algebraic variety. Yeah, so just X is a fine algebraic variety. So if it is collection of zeros, so the set of zeros of a system of polynomials So which are some kind of polynomial equations on the vector space. Yeah? Just on vector space of dimension n. Yeah, so of course, so here you have the slight problem. Yeah, so this is because the set of zeros doesn't characterize. So the set of polynomials doesn't characterize. So the set of polynomials. Yeah, I mean there is no problem with definition, but just we want to make we want to pass to some kind of algebraic geometry. So the set of polynomials define ideal, of course. So they generate the ideal, and then you can think of the set of zeros. So the set of zeros doesn't change when you pass to to the set of zeros of the polynomials that lie in this ideal. Yeah? So it is sufficient to take the generators. But of course, here you can put it to be I, and so you denote V of I is the set of zeros. But of course, this if you so if different ideals can define the same set of zeros. Yeah, so just and this the easiest example is just taking the ideal generated by x on a fine line, and the ideal taken just generated by x squared on a fine line. It defines only 0 point, and of course this is just not the unique way to define it. So we pass to radical ideals. So the Hilbert theorem on zeros. Yeah, sure.
GLN is a set that where the determinant.
Just a second, I shall explain this.
I just don't understand. Is that the algebraic group is not an affine algebraic group?
Yes. So there is just a second. I mean, GLN is some exclusion, and you shall see. So just a second. Yeah. So. Yeah, so this, if you look, but thank you very much. It is a good question, but of course, I was going to explain it. So if you, yeah, so the set of zeros is, so the ideal doesn't correspond to the set of zeros, so different ideal correspond to different set of zeros, but you can notice that if you can pass to the radical of ideal, so which is the set of elements of, yeah, so we assume that I sits in some ring A, and here you think of polynomial ring. So let us put the polynomial ring to be the ring A. So if I sits in A, you can take the powers just so the elements that such that the powers lie in this I for some k, which is natural number. I mean k is not fixed. So such that there exists k and just that belongs to n, and such that the power of this element belongs to this ideal. Yeah, so you are just looking at the radical, And of course, you see that so you see that if you are just if you have taken f and taken its power, and this vanish on this set of zeros, so then of course f also vanish. So if f vanish on x, then of course as the function, then of course fk vanish on x, then f vanish on this set. So this of course happens if you are thinking of these functions, it's the polynomial functions with values in k. And so this tells you that you can easily enlarge your ideal to characterize your set of zeros, and Hilbert-Nullstellensatz tells us, so the version of Hilbert Nullstellensatz so the theorem on zeros tells you that if K is algebraically closed field, so you do not assume that it has zero characteristics, then the set of zeros of polynomial systems of equations are in bijective correspondence. So the set of zeros of polynomial equations are in bijective correspondence with radical ideals. Yeah, so radical ideal is is ideal that coincide with its own radical. Yeah, so note that if you take a radical twice, you get the same ideal. And radical ideal is just, so we call I radical. If a radical of I is equal to I. So this means that when you take the system of polynomials, you can pass to its radical, and then it will have the same set of zeros, precisely the same set of zeros, and then you can just say that after you passed to the radical, then you already have radical ideal. So this gives you, so this gives you given the set of, so the set of points, you can of course consider the set of polynomials that vanish on this set of points, and so you can go from one side of this picture to the other. Yeah? So okay, any questions here? No? Yeah, so we had a natural question about GLN. Yeah? Yeah, so we had question. So about GLN of V, because GLN of V is defined as follows. So you consider the set of matrices such that determinant is not equal to 0. Yeah? But there is a, no, thanks. So, but there is a natural construction. So, that tells you the following. So, suppose you, so before I give this construction, I should tell something about. So we should recall the notion of the regular functions. So sometimes actually you want to, so sometimes you want to work actually with any ideal, with not only the radical ideals, but of course this notion, just explaining why this notion should be considered comes from this bijective correspondence between radical ideals and zero sets. So, so you have a collection of. So suppose you suppose X is sitting in some affine space, and X is defined by collection of polynomials. So you can think of this as it is defined by ideal I. And then you can ask what we call the functions on X. So X, we call such X closed subset. So this X is Zariski closed, is called Zariski closed, if it is just defined by collection of polynomials in a affine subspace. And so you can ask what is the natural object by for the functions on X, and one of the choices is to take polynomial functions and to take restrictions of polynomial functions to X. So we call
X is vanishing set of I.
X is vanishing set of I. So here I do not assume that I is. For a moment we can assume that I is radical. So radical ideal. But then we won't do this. So we call X. So we call F the function from the topological set, the set of points, to K a regular function. If it is a restriction of polynomial function from, if there is a polynomial K of x1 and xn, such that the function f is equal to restriction of f to x. And of course, one notices that if you have just two functions, two polynomial functions, those restrictions, so those restrictions are equal, then of course it is equivalent to say that the difference belongs to the ideal I. So that just if you have two representatives, if you know that the set of points is, so here there is some subtle moment, if you know that the ideal is radical, then you know that if, so what does Hilbert Theorem says, that if you have, so let me just write down the standard formulation. So I mean, this is also standard by but I would say constructible formulation, constructive formulation, that if you have f, the polynomial, that such that and you have x, which is the zero set of a collection of polynomials fi, then if f vanish on this zero set, then there exists some power m such that the power of this is a linear combination of gi fi, where gi are also polynomials in kf x1 xn. Yeah, so this is a standard formulation of Hilbert null Satz, and it says that if you have the zero set of any ideal, then just saying this, so this is just a general element, some element of ideal, and this means that the power belongs to radical, so it is just equivalent to say that just
This is equivalent to that f is radical.
Yes, yes. So this is equivalent that f is in radical of f1 fk, yeah? Of this ideal. So if you have the same functions, you have this restriction that you know that the difference belongs to the radical of I, but it is convenient to define the regular function to be the following. So yeah, so this means that the set of functions on x, the set of functions is just the polynomial ring modular this radical of ideal. Yeah, so this just tells us precisely this Hilbert Nullstellensatz. But it is convenient to speak on a different set of functions, which is a little bit bigger. So it is convenient for algebraic geometry or for some other purposes. So it is convenient to speak, to call the set of regular so to define the regular functions not for the zero set, but for the set I. Yeah? So to define the set of regular function for ideal for I as simply just you take the polynomial algebra and you take it modulo I. So notice, so of course here you see that if you define the 0 point by x, the set of regular functions is just kfx modulo x, so which is just k. And if you are defining, so this ideal is of course radical. If you are defining it by ideal x square, then this is not radical ideal. So from the viewpoint of the set of functions on the zero set, you should have the same answer. But if you think of this, the set of functions, this is just formed as a vector space. It is the following sum of two copies of k. However, the second copy has epsilon, and the epsilon square is assumed to be 0. Yeah, so this is the set of double numbers. Yeah.
Why is that not ring?
It is a ring. I mean, it is a ring under this condition, but I mean as the vector space.
So it's not like functions on in any sense, just formula.
I mean,
So they are equal when equally written.
what? По-русски спросите.
Раньше они были равны, когда были равны ограничения на x, а сейчас не очень понятно.
Но как бы мотивировка, что the question was that before the functions were equal when you are restricting these functions to the zero set, yeah? So to the set x. But here, of course, functions has even just here you have even so here the functions have additional data, and the additional data comes it is important for the following application. For example, you want to make an intersection of two algebraic varieties, and you want to calculate the number of intersection points. Yeah, so if you are calculating the number, so for example, you have two curves, you want to calculate the number of intersection points. But but if you just do some kind of variations of these curves, then the curves can be tangent. Yeah. So and it is so if you get a tangency here, yeah. So then a number of the points calculated naively, it really decreases. Yeah. But you want to keep the information about the tangency that occurs under this the tangency that occurred here, and that's why you so this if you think of the point as and if you think of the local equation of tangency, it will be precisely defined as the equation x squared. So so here you will see that dimension. So here you can read off the following information. So the dimension of this vector space is just 1. Yeah. So this corresponds to that the point has just that the intersection space consists of 1 point. And here you have dimension of the vector space which is 2 over k. So this corresponds to that the point was obtained by the limit of 2 points. So that's why this information is important, at least for algebraic geometry. And you may just do this example in more in the following situation. Yeah, so you can do it in two-dimensional space. Yeah, via just you can think of this as the intersection of parabola and the line, or you can just think of the intersection of these two lines. Yeah, so notice that so if you want to pass to intersection of two varieties, So suppose you have two varieties that one was defined by ideal I1 and the other was defined by ideal I2. Yeah, so if you think of radical ideals, yeah, so you, in order to form intersection, you should simply just what? You should take this intersection, the union of these equations and these equations. So which is corresponds to the taking the sum of ideals. And here you can pick up the ideal generated by x, and here you can take the ideal generated by y. So intersection point will be k of x, y. Yeah, so the ideal of the intersection point is just generated by x and y. And you will have multiplicity. So the answer is k here. And if you intersect y equal to x squared, so this equation, and y equal to 0, yeah, so this corresponds to taking this modulo y square, x square minus y modulo I. This is precisely that ring we have considered. Yeah, so this is k of x modulo x squared. And this is precisely, so the set theoretically, these are the same things. This has the same radical ideals, but the intersection, yeah, so this measures that the intersections came from the tangency. So, yeah, so we know what is the set of functions. So there is suppose you have variety x. Yeah, so this is a affine variety. Yeah, so we think of this again as something defined by the collection of equations, and we take f, the regular function, which is not invertible. Yeah, so f is not unit, not unit in the ring k of x. Yeah, so this means that f generates a non-trivial ideal. Yeah, so this ideal is not the whole ring. Yeah, because the ideal is the whole ring if and only if f is a unit. And you can consider the zero set of f. Yeah, so on so these are points on x such that f of x vanish. So the question is, so if x is a fine variety, can we supply this subset the structure of a fine variety? So can we define here? So this is a zero set. So let us put the complement. Let us take the complementary subset. Yeah. So so can we define the structure of a fine variety on this set?
What it means, like, can be.
Yeah, so I shall explain this. Yeah, so yeah, so first of all, notice that it is a complement to the set of zeros. Yeah, so we just we call so U a subset in X. So if it is a fine an open subset, the risky open. If the complement is closed, yes, so if the complement x to u is closed subset.
I will define a fine variety of this set or its complement.
What?
On X.
I mean, X is a fine variety, so it is embedded somewhere in a fine space. Yeah, so on X we can speak about closed subsets on affine varieties. Yeah, so the risky closed subsets on a fine variety. So these are, yeah, so let me take, so just, yeah, so if you take X in a fine variety, which is defined by polynomial equations, so a fine variety, so we call Z the risky closed, the risky closed if it is defined by collection of polynomials. Yeah, so just by as the zero set, as the zero set of some collection of regular functions. And the regular functions on X comes from polynomials. So just X is also a fine variety if you think of, so you can think of X as embedded in AN, or you can think of X as the set. So why we're speaking about this collection of regular functions? Because after you after you restrict your attention to the regular functions, you can just forget the information about the embedding. Yeah. So so you notice that this comes from restrictions of polynomials. So Z is just defined by collection of polynomials in the affine space where we consider X itself. Ну, то есть Z это как бы, то есть Z мы называем замкнутым позариском, и если это множество нулей набора регулярных функций, но мы знаем, что набор регулярных функций, он приходит из полиномов при вот этом вложении. И еще у вас есть набор функций, которые определяют x. Значит, все вместе точки z можно определить с помощью образующих x вот этого набора и вот этого набора.
Они регулярные на x?
Они регулярные на x, но они пришли из подъема полиномов, да? То есть вот существует жиитые полиномы, что их ограничение это просто вот эти регулярные функции. И, конечно, это... So, and of course, this set of defining equations is the collection of f1, fn polynomials, and that defines x. And this collection of G1, GL, that those restrictions are precisely this collection of regular functions. So, and notice that, yeah, so this set is an open subset. Yeah, so it is the collection of points. And a priori, it doesn't have any structure of affine variety. But what I wanted to say that we can supply this set of points the structure of a affine variety. And here I want to make an easy example. And it is one of the basic counterexamples in algebraic geometry. So it is just just hyperbola. Yeah? So and so you can take the hyperbola and project it to to A1, yes, so to the line. And of course, so what is the image of this projection? So this is everything except 0, yes. So if you take the value x, which is non-zero, you can you can calculate the value y, so you can lift it to the point x inverse. Otherwise, you cannot lift it when you have when it maps to 0. And so this is why this is yeah. So this is precisely an example that shows that the very natural mapping between the varieties. So the image of this mapping is not algebraic, not closed, for example, the risky subvariety. Yeah. So and also this shows that this allows us to give this set. So this map allows us to give the set A1 without 0 the structure of closed algebraic variety, thinking as it is hyperbole embedded somewhere. Yeah. So structure.
But isn't just like set to set projection with some variety or something more?
It is a little bit bigger than just set by set injection. It is bijection also given by the some collection of polynomials. Yeah. So this the map from this set to this one is polynomial map. Yeah. So this suggests us to introduce the regular map between varieties, between affine varieties. So regular maps between affine varieties. It is the following. So you want to. So what is characterizing property of affine variety? Sitting as a closed subset in a affine space AM. So you want to produce a map F to Y. Y is also sitting in some affine space of different dimension. So we call F regular if it is obtained as the restriction of polynomial maps. So between affine spaces, you know what is polynomial map. So you have here the coordinates x1, xn. Here you have the coordinates y1, ym. And the set, this map phi is called polynomial or regular bit just if if I j is given by some polynomial fj x1 xn, and phi is called regular if you can find such two embeddings and a polynomial map phi such that this diagram is commutative. Yes, so just phi is called regular. Phi is called regular if such diagram is commutative. So there exists such commutative diagram. And of course you learned here of course so the map between these two guys are polynomial. However however this set is not closed. Yeah? So the image of the target is not closed. So, but you may think of y to be A1. Yeah? So this should be thought as the map between x and y, where y is equal to A1 and is affine varieties. But however, you can have the map between varieties which is not surjective. Yeah? So here is the example of this map. And this bijection allows us to consider the following, consider the following construction in a general case. Yeah? So suppose, suppose x so suppose x is sitting in some affine space, and you may just think of, so you want to consider here the subset xf, which is the complement to this hypersurface f. So so of course you lift so this is a regular function, so you may lift the equation to just f is now the polynomial, the lifting of this equation to x1 xn, so such that restriction to x is f, is this regular function. And you may simply add, so as you see here, so you started from this, so this can be thought as, so the complement to 0 can be thought as the complement to the equation x equal to 0. So the complement to this 0 set, and we want to mimic this construction. So you have to add a new variable, so we want to put xf. We want to put it in new subset, so we enlarge the variable, so this corresponds to the set of functions is now, I denote the additional variable by t, and you can simply consider the following set of equations. So x was defined here by the collection f1 fn. So here you can use the same collection of equations, and then you can add the additional equation plus equation f, so this f of x1 xn times t minus 1 equal to 0. So this is additional equation. And of course, you may see what is the projection of x. So xf now sits as a closed subset here. And you may think what is the projection of this set to an. And this is nothing as Yeah, so I mean you can start by considering some subset here. Y, yeah? So defined by this collection of equation. And when you project this to an, so you notice that first of all y should satisfy precisely this kind of system of equations. And this means that the point where, so if it is projection pi, so this means that pi of y belongs to x. And then you have additional property, but this additional property says that this value, yeah, so if you want to solve this equation, this value cannot be 0, because if this value is 0 of this function, this equation cannot be solved, yeah. So, and plus condition just f of is not equal, f of y is not equal to 0, yeah. So f of y, which is f of pi of y, which is f of f small f of pi of y is not equal to 0. So because you just want to do the following operation, if you have the point here in the image, then you can lift it to the point of y. So that means that you should have you have the solution of for the equations f1 fn already, and you want to lift it to solution of the system, means that you should find t, and t is found, so given pi of y, y is reconstructed by taking the same coordinates and just adding f inverse of this function, yeah? So 1 over this function. So this shows that this subset, the complement to the collection of zeros, can be realized as the closed subset. So we have realized our GLN, the subgroup, as the group of, just as a subset, as a closed affine subset in affine space. Okay? Okay. And other, if you look at other groups, then this condition of preserving the form can be written in matrix forms. Yeah, so you may just this gives so of course it doesn't realize just the group in the matrix, but in the set of matrices plus the additional variable. Yeah? So this gives this gives algebraic structure on GLE. Or you can think of just the following. So just another construction. Here you can think of. So this is a general construction of algebraic geometry, but another construction comes from the following observation. Yeah, so you can notice that SLV is algebraic variety, yeah, because it is a fine variety because it is just defined by the determinant of that which is equal to 1. Yeah? So and how to define, how to put GLV in SLV. So the idea is to put some GLN in some SLM as a closed variety, as a closed defined variety. Yeah? So how we can put it? Who has ideas?
And on the diagonal spectrum, inversely.
Yeah, so you can put it as a block matrix. Yeah, so here you put GLV. Yeah.
Then 1 over the
Yeah, and 1 over determinant of. But you cannot put 1 over determinant. Yeah, so you know that it is. I mean, you know that this. If you put 1 over determinant, you are out of the range. Yeah, so you are putting here some element.
yes.
Yeah, so here you put the set of zeros, and here you put it as a subset of SLV. Yeah, and yeah, so the equation is precisely determinant of A times A is equal to 1. Actually, this is precisely this equation. Yeah. Yeah. I mean, it is precisely this equation, but you have additional set of zeros. I mean, we have put it in the group in a much higher, in much bigger set of matrices, and we have put the additional equations, which are collection of zeros, vanishing of the entries of this matrix. Yeah? Ну, то есть, как бы, уравнение вот это такое же, как и здесь на самом деле, но просто мы еще добавили, что часть переменных обращается в ноль, да? То есть, как бы, so, and what is the benefit of this construction? So the benefit of this construction that we have realized the GLV as a closed subgroup. Yeah, so V plus key, yeah. So this is n plus, yeah, so n plus 1 dimensional SLN. So we realized this as not only as the subset, but we realized it as a subgroup. Yeah, so we realized it as the subgroup. Okay. So just yeah, so maybe it is a good point to make a break now.
Maybe it's a good time to talk about grading and cross touch. Like we have one lecture and one seminar each day.
Yeah, so it will be from time to time. So sometimes I will prefer just having seminar, and sometimes I will prefer to have a lecture.
Okay, and grading?
And grading, it is just, I shall have the home sheets. Yeah, so this will be 30% of the home sheets and 70% of final exam. Okay.
Финальный экзамен в каком формате?
So the final exam will be in the format that will be allowed by epidemic situation in Russia. So, no, usually I prefer to have before epidemics. I prefer to have oral exam, and so I talk about. So usually I have the set of problems that I consider that are good to be solved. So the one just I give problems either from that list or that are very similar for the list I'm giving. and then just I speak about the theory, something like that. But just 3 years, I think already 3 years we are having just no possibility to have such exams, so that it will be take home. So as for me, I'm definitely sure that it will be a take home exam.
I'm kind of worried because it has like huge percent from all grade, and maybe higher school economics will force you to make factoring for this.
Factoring? So usually I put it, you mean?
Anything which is connected to proctoring is really awful if based on our experience with English. So.
Yeah, so it's not me who is talking about this. So, yeah.
We can do the exam somewhere outside. We can do the exam outside the building if they like this building.
Чего?
We can just do the exam outside the building.
В НМУ можно провести экзамен, если будет закрыта вышка.
Нет, как? Нет, ну как бы тогда будет домашний экзамен, ну как бы что делать? So if the building will be closed, then it will be take-home exam. I mean, just I do not see the other options. Yeah, so okay, so let us do the break. So just. Нет, я хотел что-то про группу уже сказать. Ага, конечно. Давайте я уберу просто.
Если на множестве идеалов